Next, we're going to look at solving problems using quadratic relations. So for our first example, we want to describe the transformations you would apply to y equals x squared in the order you would apply them to obtain the graph of y equals negative 2x squared plus 8x plus 10. The first thing you should notice is that we have an equation in standard form. And in order to look at transformations, we need to rewrite this equation into vertex form. So we're going to take this equation in standard form and then get it back into vertex form. And for us to do that at the moment, so we need to factor. And when we factor, we can find the zeros. And from the zeros, we can get the axis of symmetry, we can get our optimal value, and then we can finally get our vertex, and we can rewrite this equation here in vertex form. And then we can describe the transformation. So there are quite a few steps in order for us to solve this problem. So let's start by factoring this expression. So we have y equals negative 2x squared plus 8x plus 10. Remember, the first step for factoring is to common factor. And when the leading coefficient is negative, is also to take out the negative factor for this expression. So we're going to take out a negative 2, and that's going to give us x squared minus 4x minus 5. So for this quadratic, we need two numbers that add up to negative 4 and multiply to negative 5. And those two numbers are negative 5 and positive 1. Since the a value is 1, we can use a shortcut to give us our factored form. So it's negative 2, and the magic numbers here are part of the factors for factored form. And again, this only works when the a value is 1. Next step is to find the zeros, so we're going to let y equal 0. And we end up getting 0 equals negative 2, x minus 5, x plus 1. And if we solve for each of these factors, we have x minus 5 equals 0, which tells us that our first 0, if we add 5 to both sides, is at 5. And we have x plus 1 equals 0, which tells us that our second 0 is x equals negative 1. Next, we can find our axis of symmetry. And 5 plus 1 divided by 2 gives us 2. And finally, let's get our optimal value. And our optimal value is y equals, go back to our original equation, negative 2x squared plus 8x plus 10. So we have negative 2 times 2 squared plus 8 times 2 plus 10. So we're subbing our axis of symmetry into our equation to find the optimal value. So this gives us negative 8 plus 16 plus 10. And if we continue up here, we end up with y equals 18, which tells us our vertex is 2 and 18. And now we know our quadratic in vertex form. We have y equals a. I'm going to hold off on the a for a second. That's x minus 2 squared plus 18. And we already know the a value. The a value is given here in standard form. It is the same a value for vertex form. So instead of trying to solve for the a value, I'm just going to use the a value from standard form. And there's our equation in vertex form. But this wasn't our question. Our question was, state the transformations to go from y equals x squared to this standard form equation. Y equals negative 2x squared plus 8x plus 10. So we're going to take the equation rewritten in vertex form and describe the transformations. So starting with the a value, we can say that y equals x squared is stretched vertically by a factor of 2 and reflected across the x-axis. So it's a downward opening parabola. And then looking at the h and k values, we can say the graph is also translated 2 units right and 18 units up. And there we've described the transformations for y equals negative 2, x minus 2 squared plus 18. Example 2. Determine the equation of a quadratic relation in standard form given that the graph has vertex negative 3 and 5 and passes through the point negative 4 and 1. So there's the vertex, and since the point is below it, we have a graph that opens downwards. And if we want to find the matching point should be at negative 2 and 1. Because remember, a parabola is symmetrical about the axis of symmetry. So there is our parabola with vertex negative 3 and 5, and it also passes through the point negative 4 and 1. It wants the equation in standard form. At the moment, it's easier for us to start with vertex form because we have the vertex. So we're going to start with this. Y equals a x minus h squared plus k. And once we find this equation, we can then get our equation in standard form. So first we sub in our vertex. So that's x minus negative 3. So that's plus 3 squared plus 5. Sub in our point, negative 4 and positive 1. So that gives us 1 equals a negative 4 plus 3 squared plus 5. So let's isolate for a. So we get 1 equals negative 4 plus 3 is negative 1. We square that. That gives us 1 plus 5. And then move the 5 to the other side because it does not have an a attached to it. And we get that the a value is equal to negative 4. Which is great because our a value should be negative because the parabola opens downwards. So now what we have is our equation in vertex form. Y equals negative 4, x plus 3 squared plus 5. Again, this is vertex form. And we want this in standard form. So to do that, we're going to expand this expression. So we have y equals negative 4, x plus 3, x plus 3 plus 5. Using our distributive property, we're going to take x and multiply it by x and 3. And then we have 3, which we multiply by x and 3. So we get negative 4, x squared plus 3x plus 3x plus 9. And then outside the bracket is a plus 5. The next step I recommend is simplify what you have in the brackets or collect like terms. And then finally, we're going to expand and simplify one more time. So we're going to distribute the negative 4 into the bracket. So we end up with negative 4x squared minus 24x minus 36. And then we still have that plus 5. And finally, we get y equals negative 4x squared minus 24x minus 31. And there is our expression in standard form. All right, last example. The height of the rocket can be modeled by the relation y equals negative 5, x minus 2 squared plus 45, where, I should be missing the x there, where x is the time in seconds after the rocket was launched. When did the rocket hit the ground? Well, first of all, we have vertex form here, and the vertex is 2 and 45. We're not exactly sure what the y-intercept is, but that's okay. And we want to find out when does the rocket hit the ground. So when does that occur? Well, for us to do this, we need to get the equation into factored form to find the zeros. Right now it's in vertex form. We're going to express this in standard form to start. So y equals negative 5, x minus 2, x minus 2 plus 45. Same thing we did above. We're going to expand the x into the bracket, expand the negative 2 into the same bracket, and we get negative 5 x squared minus 2x plus 4, and then we have the plus 45 outside the bracket. Next line we get negative 5 x squared minus 4x plus 4 if we collect like terms. Again, we're going to distribute the negative 5 into this bracket, and we end up with negative 5x squared plus 20x minus 20, and then plus 45. And this gives us the quadratic relation in standard form, negative 5x squared plus 20x plus 25. So what we have here now is we have our vertex form, we have our standard form, but we still need our factored form. So remember, this question is asking us to take the rocket modeled in vertex form, and there's the picture again shown here, to find out when it hits the ground. And to hit the ground, we need to look for a 0. Vertex form does not give us a 0, it gives us the vertex. Standard form does not give us the zeros, it gives us the y-intercept. So we actually know the y-intercept now. So using standard form, however, we're going to factor and get it into factored form. So first step of factoring, take out the common factor. So we take out negative 5 and we get x squared minus 4x minus 5. Next we need two numbers that add up to negative 4 and multiply to negative 5. So those two numbers are negative 5 and 1. Since the a value is 1, we don't need to break up the middle term. We can write this as negative 5x minus 5x plus 1. Next step is to look for the zeros, and this is what we're looking for. So to solve for one of the zeros, we're going to take x minus 5 and let it equal 0. And we end up with x1 equals 5. Do the same thing for the other factor. We get x plus 1 equals 0. Therefore, the second 0 is x2 equals negative 1. So now we relate it back to the question, where x is the time in seconds. When did the rocket hit the ground? Well, it doesn't make sense the rocket hits the ground at negative 1 seconds. So we're going to take our second 0 on the graph, which is at 5, to be the time when the rocket hits the ground. So therefore, the rocket hits the ground at 5 seconds.